So hello guys, this is Jake Poo here, and I'm recording a video demo for our final project for ECE 420 here at University of Illinois at Champaign-Urbana. So for this final project, we are implementing a song recognition algorithm from Shazam, and I'm working with Luca. So first of all, let me introduce of our goal. So the minimum viable product that we will try to deliver is that we want to deliver an Android app that runs on Android tablet and can just use a audio file as an input, and after we run it, we can get the name of the song out of it. So if we have trained the database with the song before, then we will get the name of it. If we didn't have this song in the database, then it will show song not in database. And the stretch goal that we're trying to achieve is that we will build an Android app that can record from a built-in microphone, so that we can record a clip of the video from other speakers, and then we can use that audio clip that we just collected and upload it to the app, and the app will give us the name of the song, just like how we use it with the Shazam app. So a little bit overview about the Shazam algorithm. Um, it's basically trying to extract the unique fingerprint of each song. In this case, the unique fingerprint will be the peaks in the spectrogram. So as you can see on the right side, the top right side is the spectrogram of a I Still Believe, the song I Still Believe. And then we analyze its amplitude, and then we will select a number of peaks that are really strong, and by selecting the peaks rather than the other features, we can minimize the environment effect on the spectrogram, and this will be really robust against environment noise. So at the bottom right figure, you can see that will be the peaks that we extracted from the song I Still Believe, and we will use them to build our database later. um, so how do we exactly build the fingerprints from these peaks? Um, we will talk about them later in the slides. But first of all, I want to show you that in order to use these peaks as the fingerprint of each song, we want to show you that actually for each song, the way that the peaks are located are really different. That's what make the fingerprints unique, so that we can identify each song according to these fingerprints. And on the right side, this is how we do the fingerprinting. If we go back to the last slide, we are basically creating a map in a database, a key value pair store. For the key, it will be a hash. So the hash is composed of three values. First of all, um, we will find the anchor point. For example, on the right side, we can just pick this point as the anchor point, and then we will find the following number of peaks to make pairs with this anchor point. For example, if we make 10, we can find the 10 peaks strictly following this peak to form a pair of two peaks. And then for this form of two peaks, we will extract the frequency of the anchor point, the frequency of the other peak, and also the time difference between these two peaks in the spectrogram, and we will create a hash out of these three properties. And then for the value, we will use the time offset from the beginning of the song all the way to the time of the anchor point, and then also the song ID, which means the ID of the song that it's from, and that will create a key value pair, and multiple key values like this will be stored in a database. So on this figure, we can see this is how we form the peak pairs. This is the anchor point, and the rest will be the pairs that we make. So how we implemented it, we actually implemented in Python, and we have a Python server running on on a Linux server, and we created a Android app that could be a REST server, REST client to upload clips for analysis, and also a whole song if you want to expand our song database. So on the bottom left side, you can see these are the parameters for our algorithm. We picked these values because we want to. Um, this is empirical results because we experimented it with several values, and this with this set of values, it can give us some satisfying results. But we can't promise to say that these are the optimal parameters. That's for a future work. So for the implementation, as you can see on the bottom right side, this will be the structure of how the hash is created, and at the very bottom right, you can see how the value is created. What's the bit length of each field and what each field is. Um, if you don't have enough time to understand the hash value pair, then you can pause here for a minute to read our function description. But yes, in our prototype implementation, to save our development time, we didn't use any database system. Instead, we store these key value pairs in a JSON file, and every time we try to access it or just like modify it, we have to read the whole JSON file and do it. In the future studies, if we have enough time to develop it further, we will put this key value pairs in a key value store services. For example, AWS, for example, the AWS DynamoDB, or any maybe NoSQL database software, for example, the MongoDB. Those will be the options where we try to implement it in a scalable environment for a lot of traffic. But yeah, so here are the parameters for these algorithm, and I think I don't need to explain them further because they are pretty self-explanatory. So let's go to the next slide. So this will be the software architecture of our whole solution. On the right side will be a block diagram of how we go from creating the database from scratch, importing each sound and extracting the fingerprints, and also it also shows that how when we get a clip, how we go through each process to determine the source of the song and the name of it. And on the left side will be a really high level overview of how this resolution works. So on the right side, you can see that server will be based on Python. It will be running on a Linux server. And the left side, in our prototype, we implemented it in Java on an Android tablet. But if you can do this further, if you have more time, you can actually make a iOS app or just a website so that it could be platform agnostic. I think that's the advantage of our system, because the core algorithm will be running on the server. So no matter what platform that your client is on, you don't have to change our algorithm or the code of it at all to have the same performance, have the same experience. And the whole thing will be based on this HTTP protocol. If you want to insert a song, you have to use the post request. Just put the song in the body of the HTTP request, and then also include a song file name in the parameters. But forget, you don't need the parameter at all. You can just send a clip encoded in the HTTP request body, and then send it to the server. The server will try to analyze or insert this song to the database, no matter what format the audio is in, whether it's in MP3 or WAV platform, WAV format. It will try its best because it's using the FFmpeg in the background to try to convert it back to WAV for the Python program to do the further analysis. And whether it's a succeed in doing so or fail, it will always send something back to the client. If success, it will let the client know whether this song existed or whether this song is inserted into the database. But if there's an error, not only does it send back the HTTP 500 error code, but we also send back the whole trace so that you can view it from the client. So this is our final implementation and what it looks like on an Android tablet. As you can see, because of the short of time, we didn't integrate all the functionality into one app. Instead, we used two apps. On the left side, you can see this is a apps. This is a screenshot from a app called Wrestler from Google Play, and it has been open source. So if you have more time, you can integrate it with the other app that we wrote. But for this app, its main purpose is to send a HTTP request, either whether it's a GET request or a POST request to insert a song or try to analyze a clip. And then in the middle figure, you can see this is the response from the server. Um, I up, I used a clip from the song Perfect, and the server actually gave back the correct answer. But this is the third-party app. This is not the app that we wrote. On the right side, this is a really fundamental app that we wrote, trying to finish the recording functionality of our Go. So it will record a clip of the audio from the built-in speaker or a plug-in speaker, and then it will save it as a file so that we can use the Wrestler app on the left to upload it to the server and wait for the response. So for the result, it's that the REST client, we built the REST client on top of the third-party app and the app that we wrote, and then according to the slide, it says it's closed source, but through our further investigation, this software is actually open source. So sorry about that. And then we have built a database in the cloud with 20 songs using this algorithm that we wrote, and we can use this solution that we wrote to identify some clips from the song from the database, and if we feed it with the clips that's not from the songs in the database, it will give us the notification that it's not in the database. So yeah, so that's basically the demo of our project. I'm sorry that the demo could be in a rush because we're trying to meet the submission deadline. But later we will try to open source everything that we have. If anybody else is interested in developing it further, we really welcome it. And also later I will also upload another video of our app actually running on a mobile device, which is a Android tablet. So yeah, we'll see you guys later.